SwayamPrabha. Digital India. Educated India.
Yesterday we have discussed about kinetics, one example, and of course contacting we have already discussed earlier, but this is the performance equation where using this information we have to have input, kinetics and contacting to predict what is the output from the reactor. Normally the output from the reactor is the volume of the reactor if conversion is known, or if you know volume, finding out conversion. Yes. So, now I said yesterday that I would like to give some more examples of the kinetics, where we will see different examples how you can try to model the systems. We are not deriving the equations, but we just draw the figures where it will give a clear picture of our thinking, and our thinking is more important first than actually writing the equations, right. So, that is why the other day yesterday we have taken one example, coal burning. Now, we will take another example like catalytic reaction. Example, catalytic reaction. So, this catalytic reaction may be taking place in a packed bed reactor, or in a fluidized bed reactor, or even in a moving bed reactor, and FCC, fluid catalytic cracking, and they use one system, and you may say that it is fluid catalytic cracking or fluidized bed catalytic cracking, but that fluidized bed is not the normal fluidized bed, classical fluidized bed. Classical fluidized bed has the solids in the form of batch, but whereas in the FCC it is a moving bed, or in other words sometimes we also call it is fast fluidized bed. Continuously the regenerated catalyst will enter and also it will come out, that means the system should be operated beyond terminal velocities, and there is what is called another term transport velocity, and beyond this velocity if you operate, the catalyst particle will go out of the system, and during this sojourn in the reactor then you will have contact between the FCC crude in the form of vapor and also catalyst, and the catalyst will come out, go out of the cyclone, and those particles again taken for regeneration and sent back, and gas is taken outside the reactor. So, that is not actually fluidized bed, it is fast fluidized bed. So, the reaction can be, this catalytic reaction can be even in fast fluidized bed, but in all these beds our imagination is one single particle, how a single particle is contacted with the gas, or it can be even liquid, but gas liquid solid reactions are very very few. So, our imagination is we have one single particle, and we have this is the catalyst, and definitely we know that of course, it is highly exaggerated film, this thickness, and here we have the reactant going on around the particle, and this is true if I take fluidized bed, same situation. If I take packed bed, it is also same situation, one particle, and of course, this particle is contacted by another particle, but around that the gas is moving. So, if I isolate one particle and look at this, this is what is happening. This is bulk gas, this is catalyst, and this is the film. And now we have to imagine how should I model this. That means, first we have to imagine the process in our mind. This is what beautifully Einstein did, because when everyone was worried about ether, he did not worry about ether. He just imagined in his mind that do not worry about ether at all, let me take that in this universe the light velocity is constant, and everything afterwards fallen in its own place beautifully. So, like that any process when you are thinking, everything should be first clear in your mind till then you should not even put your pen and paper together. It is only imagination, and that can be when you are traveling, or that can be when you are simply sitting, or in whatever position you are, you may be thinking. Even probably as a good researcher, you should think even in your dreams. Yeah, really, otherwise you do not get ideas. So, that is the kind of clarity in the mind should come before you start, and this message particularly for the PhD scholars, MS scholars, of course even B.Tech also, when they are doing the project. In the project, most of the time we expect that something new should be added to the adding literature. That new should come first in your thinking, otherwise you do not get any ideas, right. And straight away writing equations does not mean anything, and if you understand the physical process, then for example, if you take FCC again, how the catalyst is moving, how the gas is moving, how they are contacting, what is the time for this contact, and during that time what is actually happening, all that you have to think first. After thinking, what normally we try to do is that we will try to put on the paper qualitatively. That is what we are doing now. This is the qualitative treatment. So, I have imagined that I have particles and I have gas, and the gas should contact the solid, and if it is porous particle, it has to even go inside the particle for the reaction to take place. And once I imagine that process, now I would like to put this information in the form of some equations. So, that is why we have to first draw this figure, and now this can be imagined as the reaction steps, how the reaction should take place. I have the catalyst, and surrounding that we have the gas, and we know that again fluid mechanics will tell me that whenever you have this kind of heterogeneous system, at the interface you have the films, then the reactant gas has to go. I mean, if I just say that I have A going to R products, simply very simple reaction, then reactant A has to diffuse through the film, and in the bulk of course we do not expect any diffusion, and then we will expect a lot of diffusion, so that you will not have any concentration gradient, and then it has to go through the film where there is some resistance, and you may have slightly a different concentration in the bulk, we call that one as CAG, and on the surface it is CAS, right. So, this is the process, and from here it can even go inside the particle, right. So, now what are the steps? Yesterday also I have told you about the steps. What are the steps now? Step 1 is mass transfer of A through the film to reach the surface, and step 2 is to go inside the pores. You may have pores like this inside the pores all around, and then during the movement of these molecules through the pores, then they may get absorbed on the surface. Then after getting absorbed on the surface, then the reaction takes place. After reaction, they cannot sit there. If they simply sit there, there is no use of that surface, because only product is there, it is not allowing the reactant to go and sit on that. So, they have to naturally dissolve, they have to come out. What is the reason for dissorption? Because the concentration outside of the product concentration outside is less when compared to the product concentration here. By natural phenomena called diffusion, because of the concentration gradient, it will try to come out. So, through the pores it has to come out first, and then through the film. So, dissorption and product coming back through the pores to the surface, and from the surface into the through the film to the bulk. These are the 7 steps, right. Now, as an engineer, now you can try to simplify many things, like for example, I will assume that I do not have a porous particle. What are the steps that will not be there? Adsorption, dissorption will not be there. Diffusion of the reactants into the pore, and also product coming out of the pore is absent. Adsorption, dissorption will be definitely there, but now it will be only limited to outside surface. So, and that is one assumption. As an engineer, I can always try that, because my mathematics are going to be very complicated. Okay, let me try porous particle, non-porous particle, right. So, out of 7 steps, now 2 steps we knocked out. So, now generally what we imagine is that adsorption, surface reaction and dissorption, all 3 also we will imagine that, because all 3 will give me a rate equation. That is what we call Langmuir-Hinshelwood kinetics. If I take purely adsorption, desorption, surface reaction, right. So, it gives me only minus R A rate equation. What I imagine is that I am not also taking all that, because I know already, because of all these 3 steps I have a rate equation minus R A. Now, how many steps are there? Only 3. What are these 3? I have now film, through the film the reactant going, and then we have the surface reaction. Surface reaction now contains adsorption, desorption and reaction, right. So, the surface reaction only one step, and afterwards from the surface the product has to come into the bulk again through the film, only 3 steps. So, now again my assumption is that this is irreversible reaction. So, now how many actual steps I have? 2. What are the steps now? Yeah, mass transfer. We do not say that one as normally diffusion, because around the film or through the film convective flow also will be there around that. That is why we will say that we normally mass transfer, and you know the difference between mass transfer and diffusion. You know, the diffusion is purely by molecular phenomena, it is only by concentration difference, and whereas the convection and diffusion together in mass transfer, normally mass transfer equation, when you say we have both diffusion and convection together. I think I gave you this example, or shall I give once more this example? Like again I was telling you that if I have a lot of perfume on my body, and now this room is very still, right. So, and if I stand in the middle of the room, then the perfume will diffuse by concentration gradient, because there is no movement of the gas at all or air in the room, because there are no fans, right. So, then it is by natural diffusion, the concentration gradient, and if I stay there and then try to find out the time, the person who is sitting in that corner will smell maybe in 5 seconds, right. So, someone came just behind me and then he put a big fan, the fan normal maybe a standing fan. So, then that will now push more amount of perfume from my body by convection, and over the convection definitely you have again the original diffusion. So, that is why in any flow what you have is convection and diffusion in the mass transfer, but most of the time whether the diffusion flux is more or convection flux is more, we have to decide as an engineers. I will now ask you the question, in plug flow what is the component you are taking? Is it convection or diffusion or both? Plug flow we have defined. Sorry, what is that? I mean, what is that we have really taken in a plug flow? Pure convection we have taken. That is why we are telling flat velocity profile. Otherwise, the velocity profile is not flat, it will be slightly moving like this. That is by natural diffusion. Okay. And of course, a little bit of turbulence where back and forth it is moving. Natural diffusion means you should be slightly forward, because it is as if, another example, most of you would have seen the conveyor belts now in airports, where you can just stand there and then it will take you, right, in the conveyor belts, and even supermarkets and all that, they have the belts, escalators they call. Okay. So, if you are just standing there on the conveyor belt, that is pure convection. If you are walking on that, then that is convection plus diffusion, and the velocity what you are measuring is with respect to floor, which is stationary, right. And with respect to the conveyor belt velocity, if you are walking, that is your diffusion. So, in reality with respect to wall, if you take wall is stationary. So, if with respect to wall you take, in the reactor you will have diffusion and convection, and for plug flow, because we are not allowing any axial mixing. So, we will say that I have pure convection, that is why you have the flat velocity profile, right. So, that is the reason why this mass transfer and diffusion we have to separate, and mass transfer what is the equation and diffusion what is the equation. mass transfer, what is the equation for flux, or diffusion, what is the equation you use normally? Yeah, that is Fick's law, gradient into diffusivity. Whereas for convective flow or mass transfer, normal mass transfer, yeah, concentration difference is the flux is directly proportional to concentration. There is no gradient there, concentration difference, and that proportionality constant you are taking as mass transfer coefficient. Okay. So that is why whenever there is a chance, I would like to tell all these basics as many times as possible, so that you will never forget at least these basics, right. So that is why the first step, mass transfer, is characterized with, now this can be modeled with all the assumptions only with 2 steps, and then if I write those 2 steps, again mass transfer I am simply writing equal to reaction. And of course, here it is hidden that mass transfer of reactant through the film to the surface equal to this rate of reaction on the surface. That is what is at steady state. Yeah, Narasimha Reddy.
Particles are porous, but molecular size will be greater than the pore size.
Yeah.
Where the reaction will take place?
On the surface,
Outer surface.
because outers also you have surface. Only thing is, if you have porous particle, you have lot of surface inside available. I have been telling I think sometimes it is in 1 gram of catalyst, depending on the pores, and then how do you design this one, you will have 1 football stadium inside this 1 gram, the area of the football stadium. Okay. That is why ambitious people, as ambitious, we will always take porous particle, but how in how many ways one can model the system, I am trying to tell you, and it is not totally unrealistic model, because whenever you have noble metals like platinum particles are used and they are not porous, and all the reaction is taking place on the surface, and platinum wires are used, wire gauzes are used as the catalyst, which is just stacked inside the reactor. That is also one of the wonderful reactors. I think this is for in nitric acid process that is used. I will also mention that out sometime when you are talking about mass transfer coefficients. So, but here the assumption is that how simply one can model, and as engineers we should model as simple as possible, but nearest to the reality. We cannot have totally unrealistic things like our all movies. Most of the movies, 99% it is unrealistic. Hero hits like that, 100 people will fly. I think 100 people flying is impossible. I think no human being here on this planet can do that. It is only Superman has to come here, right? Only he can do, probably, if he is existing. So all these unrealistic, that is why model also should not be so unrealistic, but all of us clap when 100 people fly. So because we also like unrealistic things here, because we are not able to do the realistic things. So at least unrealistic things I think we are happy with. That is what is fascination, yeah. So that is the reason why the model should be as close as possible. Again, beautiful sentence, Einstein said that it should be as simple as possible, but not simpler. Okay. But reality we have to be very close to for this in this modeling. That is why. And when I assumed all this, I am not very far, because if I do not have these porous particles, there are many situations where non-porous particles are also used for catalytic reactions. So that is the reason. So once I have these 2 steps, rate of mass transfer equal to rate of reaction, then of the reactant A, then the equation again minus RAOB, this is the overall rate. This also you should not forget, minus RAOB. All heterogeneous systems will have only observed rate, measured rate, overall rate. Different books use different names for this. And if you do not have mass transfer at all, and the reaction is taking place on the surface somewhere where there is no mass transfer effect at all, so that concentration is also equivalent to bulk concentration. And if there is no mass transfer coming into picture, and the system, the reaction is not affected by any external factors like mass transfer and heat transfer, then what you have is an intrinsic rate of reaction. That is the difference between intrinsic rate of reaction and overall rate of reaction. Overall rate of reaction takes into account our the transport processes like external heat transfer and mass transfer, right. So overall rate of reaction and the intrinsic rate of reaction. So, this is the overall rate or observed rate or measured rate, this is what normally we write. ROB equal to this equation already you know, Kg Cag minus CAS, and okay, I think in between I have missed something here. The model for this, for writing this equation, that part I have. Yeah, this is catalyst, and then this is the film, and yeah, this is CAG, and in general I may have this one as CAS. It is exactly same as yesterday's example what we have taken, correct, no? So, that is why this equation also is KS CAS, and this is equation 1 and equation 2. Yeah. So, in this case if I take now the rate expression like yesterday minus RAOB equal to CAG divided by 1 by Kg plus 1 by Ks. Okay. So, this is equation 3 for catalytic reaction. Now, I will ask your brain to open and then just think about this equation and yesterday's equation, both are same, right. Yeah. But is there any other factor coming when compared to catalytic reaction and non-catalytic reaction? Just think in the process. I have a coal particle. I have a coal particle where
in catalyst the catalyst is not reacting, while in coal the coal is reacting, taking place in the reaction.
Yeah. So, then what happens? I mean, what is there any change in this equation? Yeah, because I am using the same equation for both the cases, right. Yeah. And is there any parameter which changes with the phenomena what you are describing? You are telling that catalyst will not change with time, because yeah, Ks changes, which one will change?
The thickness Kg.
Yeah, Kg will change because now Kg depends on the size of the particle also, right. And again, how do you find out Kg as a function of size? Yeah, yesterday's equation. If I have a single particle, from yesterday's equation what I have drawn there, the Ranjan-Marshall equation, Sherwood number equal to 2 plus something. You can now say that for very small particles, there are two terms in yesterday's equation, Ranjan-Marshall correlation. Okay. So, those two, anyway, let me write again that one, Sherwood number equal to 2 plus 0.6, Reynolds to the power of 0.5 and Schmidt to the power of 1 by 3. This is the equation what we have. And now imagine if I have very small particle, then I can neglect this term when compared to this 2. Then that means Reynolds number is small because of the size. Maybe I am using 1 micron particle, and catalysts are used as 1 micron particles also in fluidized beds, and even in FCC they use around 100 microns particles, because they have to transport out and all that. So, that is the reason why, and in slurry reactors also it may be 50 microns, 100 microns like that, and that is why this Reynolds number may be very small, and then in comparison to this 2 term, all this product may give me maybe 0.01 as an example. So, 2.01 and 2 I think does not matter for me, I will take 2. So, that means now you can find out what is the relationship between dP, how Kg is varying with dP. This totally neglected. So, then I have here Kg dP by diffusivity, then you will know Kg is inversely proportional to dP, right, because dP will come down here. Okay. I think maybe people are blinking. So, that is why I think I will write this one as Kg dP by d equal to 2 when that is 0. I am just neglecting that. So, then this gives me Kg is okay, inversely proportional to dP. So, similarly, I can also now say that yes, I have now large Reynolds numbers. Now, 2 can be neglected when compared to this product. So, then I can also now find out, because remember here also you have dP. Schmidt number, of course, he also has dP. No, okay, good. Yeah, and so this dP you have to, this is dP to the power of half, 0.5. Yeah. So, from that also you can find out how kg is varying with dP. You may start with big particle in the beginning, okay, in coal combustion for example. Slowly the diameter is changing. So, that means kg also is changing. So, that variation you have to take into account in the design. Only to have that difference, I thought I will also tell this one. That means, you may have the same equation, but unless you understand how the process is taking place, we cannot really appreciate all this, and these things have to be taken into account. That is why most of the time it is our brain which will give the clarity for us. Think, 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 but unfortunately in our education system we are not giving you any time for thinking. Okay? Immediately quiz 1 starts next week, and you are always worried about which aspect of this will come in the examination. So, that is why I think someone was telling in India that in India we have only exams, but no education. Really, because I think all the entire thing whatever we talk, and then entire thing what you also convert most of the time in the form of examination, whether this is coming in the examination or not. That is only the problem all the time. Okay. So, that is why you have so many things here which we can always, this simply depends on how deeply you are involving in the thinking process. That is what I think most of my lectures will be only to make you that mindset different, okay, that thinking more like that. So, that is why one has to take care of all these things, and for that initial process is very good thinking. That is why I think the first one semester for PhD scholars should be given only for thinking. You should not have, I mean you have to be fed and kept in the hostel or whatever, wherever you are, okay. But I think if you are in the hostel most of the time DC++, that is not, DC++ should be removed, and then just allow you to think. This is wonderful, and then you come up, and even without writing an equation I can always write like this, this profile, and you can also say that okay, I have a packed bed, reaction is going on, I would like to, it is exothermic reaction, right, and now so many assumptions in your mind. That is why always thinking, and we can also say that yes, I have adiabatic packed bed reactor, exothermic reaction. So, can I now plot along the height of the packed bed the concentration and temperature profiles? Can I also plot temperature and concentration profiles across any cross section, right, and is a packed bed. So, that means packing is inside, which is a solid. Can I also imagine how the concentration varies inside the particle, and how the concentration varies between the particles, because across that it is not uniform everywhere, and also I may imagine how the temperature is changing. So, that means if I have a single particle like this, can I draw the concentration and temperature profiles across all these? So, if you are able to imagine all that in your mind, then automatically I tell you that you have clear picture of what is to be expected mathematically. Okay. In engineering always mathematics come when you have to quantify something, you have to say in terms of some numbers, either 50, 60 or 100. How do you know 50, 60 or 100? So, you have to use equations, calculate, and then say that it is either 50, 60 or 100. But before that all this process should occur. In fact, my PhD students also I used to tell them that when the problem is given, you have to understand, and then you have to draw the graphs on your own without even doing any experiment. It is not that easy, like I told you, packed bed. If I ask you to draw the profiles in the packed bed, temperature profile and concentration profile along the length and across the cross section within the particle, right. So, now you draw them and then keep it in your diary, go actually for doing the experiments, and after doing the experiments compare what was your imagination and then what you actually got by experiments and also through calculation, modeling and all that. If you are thinking and if that is exactly matching, then you are an excellent research scholar, because you should visualize the entire process in the mind first and then able to convert. This is what all the great scientists did. I mean, for example, again Einstein everyone tells, but Einstein did only that. I think simply sitting in that Switzerland patent office and then thinking about the universe, and he could get the beautiful ideas. Okay. And also this is the mistake all of us do as researchers, we simply believe what has been published till this point. Okay. Based on that we try to visualize what is happening, but you have to question now, till now whatever is available is right or wrong. Again Einstein example. So, till then people who are fighting for ether, there is something called ether, everything is moving relative to that, all kinds of things they were thinking. This man said that throw away ether, and only one assumption, that the light velocity in the universe wherever it is constant. Okay. So, based on that when he started deriving, everything has fallen beautifully, and then ether has disappeared. Till then people are imagining ether is there, that is there, this is there, various mediums, and then finally now this is the reason why we remember always Einstein, because totally different thinking. You have to also do that. That is why I think all PhD scholars, particularly because other projects are only term bound projects. So, whatever they have to do, they will do just within that time, but for PhD scholars there is no end, but you can do 10 years also. Okay. Yeah. I mean IIT gives only 7 years time, but yeah, but I know the reason what I am trying to tell is that you should not believe the literature. That does not mean that you should not see literature at all. That is what, no, always we try to misinterpret things. Oh, okay, what is the point in seeing, but anyway I am not believing it. No, you have to decide whether it is right or wrong, what is right, what is wrong, what is correct, how the people have done, whether it is accurately evaluated or inaccurately evaluated, and if something is missing, that is what where you have to fill up. That is what you have to do. All of you have to do PhD in fact, because that gives you more time for thinking. The all other of course MS and PhD, all other courses, coursework programs will only drive you for examination, really driving you for madness. So, that is why more time and then more thinking will give you the clarity first. Okay. So, let us now take another example. This is catalytic reaction. Okay. So, if I have a gas liquid reaction, another example, gas liquid reaction, right. Again you know what kind of reactors we use for gas liquid reaction. We use what are called bubble columns, right. So, bubble column normally can be shown something like this. I have yeah, it can be simply liquid may be continuously coming, this is liquid, liquid may be continuously going out. Then we have gas entering, gas is coming out, and we have the liquid, and we also have bubbles. Yeah. So, this is liquid L, I will write, and this is gas. Okay. Now, how do I model, how do I imagine what is happening? Liquid is one of the reactants and also gas is another reactant. So, I can write this one is Ag plus Bl, okay, small l I will write, giving me product. Again I am taking a reversible system. Okay. Now, how do you imagine? Naidu, can you tell how do you really imagine this, the process? That means you can now see what is the the procedure for this imagination. First of all, I should know what kind of equipment I am talking. So, gas liquid systems we can have bubble columns. Okay. So, then using this, how do I imagine my process that is taking place inside this? Bubble is the gas, that is one of the reactants, and then the liquid, and in the liquid you would have seen, all of us would have seen, I think 99% of us would have seen how the liquid, how the gas moves in the in liquid, aquariums and many things we can see, or your soda or Coca-Cola, right. You have the gas inside stored, the moment you open it will try to equalize its pressure inside to the atmospheric pressure. So, bubbles will come out. Okay? Yeah. So, you should have seen bubbles and liquid, that is what I mean, that is why I am telling that example. So, how can you imagine this process?
Gas is diffusing through the bubble,
Yeah,
through the to the liquid. So, reaction is
taking place. Okay, good. So, I will now again imagine that I have one single bubble, almost spherical bubble, but most of the time this is the realistic bubble. So, this is bubble, gas, and all surrounding I have liquid, right. Yeah. And then in the process we also imagine that we have a gas film inside the bubble. So, now I can imagine this in terms of my profiles, that I have liquid here, I have first interface here, this is the interface, then we have here gas this side, then we have liquid, right. So, bulk liquid may be somewhere there, but here I have liquid film surround, that is the spot, this is the liquid film. Okay. So, this is the liquid film. Then here I have noted also I have gas film. Yeah. Right. So, now this is bulk liquid, bulk, and this is bulk gas. Right. Now, we have to draw the profile first before writing the equation. So, I know that inside everywhere here I have the same concentration of gas. So, I may show that one as like this CAG. Okay. So, now this has to go to through the film, this is CAI, okay. Yeah, CAGI. Okay. Good. So, now it touched the interface, that is the liquid, gas liquid interface, sorry, gas film I have not drawn. Yeah, this is gas film, this is liquid film. Yeah, here I am sorry, here we have CAG, then I have CAGI, this is the gas liquid interface, GL interface, and at this GL interface we have what is called Henry's law. What does that tell you? Okay, gas has reached this film, and afterwards this gas has to dissolve in this liquid film that at that interface, and then it has to diffuse further in the liquid. That means, liquid concentration, the A, how much that is dissolved inside the liquid, that has to diffuse through the liquid film. So, that is why depending on your Henry's law, it can be either top or it can be either bottom. So, that means, here I have now CALI, maybe at this point I have CALI, okay. And from here again this will come here. So, this will be CAL, and from here it may be constant. Please remember, this connects, these two are connected by Henry's law, CAG, CAL. Okay? Yeah, those two are connected by your Henry's law constant. So, this is the profile. Now, I have to draw, I have to write now the equations. Yeah, and now again you have so many assumptions here. That is why deeper and deeper when you think, you will get more and more information. What are the things? Simply saying that okay, I have, this is the bulk and I have here the film, and then at the interface it will reach thermodynamic equilibrium, Henry's law constant. From there it will diffuse and then go to the bulk. Where is the reaction taking place? Yeah, this assumption is that it is inside the bulk. It need not be. If the reaction is very fast, where the reaction takes place? Almost at the interface, because it does not have time to even diffuse here, or if it is relatively slow, most of the reaction may be taking place only in the film. Okay? Right? And if it is further very slow, then where the reaction taking place? Entire bulk. At that time, your batch equations are directly useful there. See, it is heterogeneous system, but the presence of gas will only occupy some volume, but it is not really reflecting in the rate of reaction, because rate of reaction is so slow. Then the reaction is taking place through the entire liquid. Okay. So, you need normal batch reactor design expressions for that condition where you have the very slow reaction. If you have very fast reaction, most of the reaction may be taking place on the interface. So, that is why to exactly find out what is the reaction rate, because it is interface, you have to very accurately estimate what is the interfacial area, between gas and liquid, right. There are few methods available to measure interfacial areas. That is why in heterogeneous systems, whatever you have to think, the limitation is only your mind, and of course, you have to also find out which one is faster, which one is slower and all that, right. And most of the time when I have the bubble phase here and then the liquid film, this is the bubble gas film, this is the liquid film, that is what is given here. Most of the time we neglect this part. Why? Neglect in the sense that we assume that there is no concentration gradient inside the bubble. That is true particularly if I have pure gas. If I have two gases and only we are talking about A diffusing through B, our assumption is that all the resistance is in the gas film near to the interface. But if I have only pure gas, most of the time we use pure gas, for example, hydrogenation of vegetable oils, this is also one of the very good pictures for that too. So, then if I have that kind of assumptions like pure gas, then this will disappear totally. So, then I will have only liquid film which is coming into picture, right. So, with these assumptions one can now write the actual equations like we have developed the rate observed. Good. Another example which I give is slurry reactor. Imagination, I have the reactor first, I have the particles, we have the bubbles which are fed like this, these are the bubbles, and then in between I have liquid. So, this is gas phase, this is liquid phase, slightly exaggerated solid phase. Okay. Now, here also I have not discussed about this one, this particular one. Here I have taken liquid is continuous, gas also is continuous, but in fact here I can have liquid as the batch, right. The moment I have the liquid as the batch, I do not have to worry whether it is plug flow or mixed flow. because it is a batch system. But the moment I have the gas as continuous system, then I have the plug flow. So, similarly here I can have liquid batch and also solid batch, gas is only continuous, and most of the time we take it as plug flow. Now, my imagination is that I have okay, we have the particle, sorry, we have the first bubble, surrounding this we have the film, inside also we have the film, and here I have the particle, here also we have the liquid film, right. What are the steps now? The gas which is inside the bubble has to first go through this film, then at the interface, from interface to the liquid film, yeah, this is all liquid, right. So, assumption is that liquid is sufficiently mixed. So, that is why the gas dissolves here faster and then no concentration gradient, and then finally, it has to come through this film and go to the surface and react on the surface if it is only non porous particle. If it is porous particle, again it has to go inside. Very quickly drawing. Now, I think you definitely know about all these things. So, I can simply draw this. Yeah. So, now inside the bubble till this gas film, I have a flat profile, okay, and at the interface, this is the interface, there is some drop, and from there again depending on Henry's law constant there is another drop, okay, and from here it is almost constant, and again from here you have the drop, and if it is porous particle you have again the drop, right. Again if I write this thing, this is CAG, this is CAGI, this is CALI, this is CAL, this is also CAL, this is CAS. If it is non porous, then this concentration Ca as a function of r, where r is the diameter radial distance inside the particle. If it is non porous, then this is stopped, this beyond this it is not there. So, all these steps we have to take into account. Now, you see step 1, Anurag not able to follow? Yeah. So, because I explained those things so much, so I just went a little bit faster here. So, then the first step is mass transfer through the gas film within the bubble reaching interface, from interface to liquid film, that is liquid side, but surrounding the bubble. Then inside the liquid I have same concentration because of vigorous mixing. If the vigorous mixing is not sufficient which has been created by bubbles, then we will also put a stirrer. Okay. Stirrer also will help the solid particles not to settle. Okay. So, that is why sufficient mixing we will create. So, this concentration is almost same throughout the liquid. Then it goes to the surface of the solid, the film surrounding the solid, that is CAL. Then from there it goes to surface CAS, and then this one, and this entire thing we model in terms of effectiveness factor.
The slope in the solid won't like the slope for the drop of concentration here and then inside the solid won't be same, sir.
It won't be same. It won't be same. That is why I have just shown a little bit of curvature there, like this. Because if it is a spherical particle, we can solve that and then it will come like that. So, the concentrations are analytically just drawn, but not the real shapes, but still I wanted to show the difference. So, I have shown it here. So, all these concentrations we have to evaluate this and then finally, we can express in terms of measurable concentration of the gas phase. That is one possibility. Other possibility is also using the rate based on volume of the liquid. These two possibilities are there in this, right. So, that is why in heterogeneous, how do you define the rate also is very important. So, in the next class I will tell you how do you define the rates, what are the possibilities for the rates, right. I think I have already told you once, but let me also write those equations, then you will have a clear picture of under what conditions you have to choose, it only depends on your convenience, right. So, this is one example. I can also come out till here and then say that yes, I will now express based on gas phase, bubble phase, or I can also express based on liquid phase or total volume. It depends on how do you what you like and what is the simplest one. Okay. We will stop here, and the next class we will discuss all this.